Hello students, today we are going to see the basics of cells. Okay, if we take a battery, a cell, okay, what is actually cell, what cell does, all these things we will see today. Then about terminal voltage and the calculation of terminal voltage on various occasions like open circuit, short circuit. Okay, then when we charge a cell, when the cell is discharging. Okay, then combination of cells if we connect in series, cells if we connect in parallel, all these things will come inside this topic. Okay, so how much you will be able to cover today, that much we will be covering. Okay, so cells. So suppose if we take a cell, okay, we have seen this symbol, okay, so and we used to put this is nothing but EMF. Okay, what is EMF? Suppose if we connect a cell across a resistor, then what will happen? Current will start flowing through this. Why current is flowing in this direction? Because electrons will be flowing in this direction. So cells do not supply electrons. Cell is not a supplier of electron. Okay, the electrons are already there in this resistors, even in this wires also. Okay, free electrons are already there. What this cell does is it gives energy. Okay, it gives energy to the electrons to move. Okay, to move around the circuit. Okay, so cell provides energy to electrons to move around the circuit. This is what is happening. Okay, so what it does, if we take this part, that is this cell, what is this actually? This is battery, and where chemical energy will be converted into electrical energy. So two electrodes will be there. Okay, so these electrodes will be dipped in electrolyte. So here this is going to be positive terminal and one will be negative terminal, and across this resistance is connected across these two electrodes. This is what is the cell. Okay, so when what happens is, from this terminal electrons will be coming here, so electrons will be accumulated here, electrons will be here. So from here electrons doesn't want to go to negative terminal again. Okay, this is electrons are negatively charged particle, and this terminal is also what? Negatively charged. So here these electrons and this positively charged particle, positive electrode, okay, there will be force of attraction, which is nothing but electrostatic force. But this chemical reaction, okay, redox reaction that is happening here, okay, oxidation and reduction, the redox reaction that is happening in the cell, okay, make sure that these electrons will be coming to this electrode, from positive electrode to negative electrode. So that is called we say force provided by battery. So when the force provided by battery is more than F electrostatic, okay, then electrons will be moving like this. So from here again this process will happen. So what happens is chemical reaction chemical reaction, that is nothing but redox reaction. Okay, redox reaction will bring, okay, we call them battery mechanism, okay, will bring energy to electrons. Clear? Okay, so what happens is work is done on the electrons. Work is done on the electrons. Work is done by cell on electrons to move from positive electrode to negative electrode. Clear? Now once if it reaches here, again it will circulate. So that is what is EMF. So EMF is nothing but work done. EMF is work done. What? EMF is the work done per unit charge. EMF is the work done per unit charge. Okay? Clear? So suppose if we draw a cell, okay, this is EMF. So we can say EMF is the potential difference across the terminals when no current is flowing in the circuit. Okay, if there is a current flowing in the circuit, if we measure the potential difference, say if this is an external resistance, okay, definitely there will be an internal resistance also in the cell. How that is? Suppose again if we take electrodes, for electron to move here, for electron to come here, if electron is coming to this direction, the current will be moving to this direction. So one point is, generally we have studied current flows from higher potential to lower potential. Okay, in the circuit. So this point we should remember. Current moves from higher potential to lower potential inside the circuit, but current flows from lower potential. What is lower potential? Lower potential means negative electrode. Okay, from lower potential to higher inside the cell. So inside the cell, the current is moving in which direction? From negative. From here, if we magnify this, okay, it is moving in this direction, current. But otherwise current is moving from positive to negative outside. Inside, current is moving from negative to positive. Okay, so based on the condition, the current flows from higher potential to lower potential will change. If it is outside the circuit, this is correct. Inside the circuit, this is correct. Okay, right. So when current moves in this direction, if this is negative and if this is positive, electron doesn't want to come here. Work will be done on this electron by the cell, by the battery mechanism, by this chemical reaction to come to positive electron. When it try to come, okay, the current will be going in that direction, from positive to negative. So when current goes from positive to negative terminal, inside the cell, there will be some obstruction for that also. There will be some obstruction for that also. That is called internal resistance. Okay, that is called internal resistance. Okay, note it down. We will discuss about internal resistance also. Okay, so internal resistance. Okay, what is internal resistance? Resistance offered by electrolyte of cell. Okay, resistance offered by electrolyte of the cell. Okay, and it depends on, first thing, nature of the electrolyte. What kind of electrolyte we choose? Directly proportional to concentration of the electrolyte. Okay, then directly proportional to distance between the electrodes. Distance between the electrode, directly proportional to distance between the electrodes. Then it varies as the common area of electrode immersed in electrolyte. Area of electrode, okay, immersed in electrolyte. Okay, depends on that. Then inversely proportional to temperature of the electrolyte. Inversely proportional to temperature of the electrolyte. Okay, so internal resistance depends on all these factors. Okay, so internal resistance, where do we mark? We mark like this. Okay, copy this. Copy these details. Suppose internal resistance we mark like this. This is actually not a circuit kind of materialistic or wire related resistance. This is the resistance offered by the electrolyte or solution inside the battery. So actually this is like this. We should have given like this. Okay, that is, this is the resistance, resistance offered by what? Offered by inside the battery. Okay, this is how this resistance, internal resistance, is inside the battery, but as a convention we follow like this with a small resistance R, and EMF we will be marking as E. Clear? So EMF is nothing but, electromotive force is not a force. Okay, previously they thought that this force is making the current to move. Okay, later they came to know that it is the work done by the cell to move the charges across the circuit. Okay, so electromotive force is nothing but the work done per unit charge, work done on unit charge, okay, to move it around the circuit. So EMF is the work done per unit charge to move the charge around the closed circuit. Okay, so we can say EMF is equal to work done divided by charge. Okay, we can say EMF is equal to work done to maintain it in the closed circuit divided by unit charge. Okay, so this is one definition of EMF, one definition of electromotive force. Note it down. Okay, another definition is EMF is the voltage difference. Okay, what is the unit of EMF? Unit of EMF is volt. This is volt. Okay, not Newton. Okay, this is volt, not Newton. So work done per unit charge. Okay, so joule per coulomb, when it comes, it will be volt. So internal resistance is there, okay, internal resistance is there, and then if there is an external resistance, suppose if we are giving 9 volt, if this is 2 volt and this is 1 volt, then how much current will be flowing through this? I is equal to E by R plus R. We will be getting 9 by 3, this is going to be 3 ampere. So if 3 ampere current flows, okay, like this, then there will be a drop of 6 volt potential drop is there. So suppose if we try to measure the voltage across this point, what will be the voltage you will be getting as, or potential difference you will be getting as 6 volt, which is not equal to 9 volt. So when the current starts flowing, or if we connect the circuit, then the potential difference across the terminal, this potential difference A, B, the potential difference across these two terminals is same as here. So potential difference across the battery or potential difference across the external circuitry, external resistance, both are same. So if the current is flowing, then this 9 volt is different from this. Okay, so if the current is not flowing, if we measure the potential across this, we will be able to get 9 volt. Okay, if the current is not flowing. So based on this, okay, just because this external resistance is connected, when the current is flowing, here one drop is there, here one drop is there. You can see when the current flows like this, plus minus, here also a 3 volt drop is there. So E is coming as, if we name this as terminal potential difference, Vt plus V of small r, or we can say EMF is equal to voltage across external circuitry or external resistance plus voltage across internal resistance, okay, R. This is what is actually EMF, or EMF will be distributed across all the resistances. So this is one thing. EMF is nothing but the sum of voltage across external resistance and voltage across internal resistance. Note it down. Okay, now suppose if we remove this connection, if we measure here voltage, if we measure a voltage here just by using any voltmeter, this will be showing 0. Now no current is flowing across this, no current is flowing in the circuit, correct? No current. So means no voltage drop here. Okay, so no voltage drop. If the same circuit, if we measure voltage across the cell, okay, if we measure the voltage across this cell, okay, we will be able to get what? 9 volt. If we are in a position to measure the voltage across the cell alone, okay, definitely this will come inside. Just for a representative purpose, we are drawing like this. So if we are able to measure, okay, we actually, if there is no current means no voltage drop here also, but for understanding purpose we are discussing like this. Now if we are able to measure, this will be getting as 9 volt. So from this we will be getting, okay, you have noted down this, right? Copy this. From this we can say another definition like EMF is the potential difference. EMF is the potential difference across the terminal of battery when no current is flowing. When no current is flowing. When no current is flowing. Okay. Or when the circuit is switched off. Or the circuit is switched off. Clear? EMF is the potential difference across the terminal of battery when no current is flowing or when the circuit is switched off. Okay, clear? So far we have seen about EMF, internal resistance. Internal resistance is the resistance offered by the electrolyte which is inside the battery. And EMF is nothing but the work done per unit charge in order to make the flow, in order to make it run through the closed circuit. Okay, EMF or battery is nothing but the energy provider. Another thing is EMF is the voltage difference or potential difference across the terminal of two batteries. Terminal of batteries. When we say terminal, this is nothing but it includes like this. This is the terminal of the battery. Okay, when no current is flowing. When current flows, what happens? There will be a drop across external resistance. There will be a drop in the internal resistance also. Okay, this is the definition of EMF. Right. Now we will see terminal voltage. Terminal voltage or terminal potential difference. Terminal voltage or terminal potential difference. Suppose when we connect a cell to an external resistance, this is EMF and this is small r, what will happen? Current flows like this. So if we take these terminals, just like what is the terminal of battery? This is how. So same terminal if we take, this is same. Now when no resistance is in between, we can say this is A, this is B. Here it is A and this is B. So same terminals. This is same terminal. Only difference is an external resistance is connected. So when external resistance is connected, current will flow. Same example we have taken. This is 9 volt. If this is 1 ohm and if this is 2 ohm, what will be the current flowing? 3 ampere. So voltage across this 2 ohm is going to be 6 volt. So terminal potential difference or terminal voltage is nothing but this 6 volt. 6 volt. So if we take current is flowing in this direction outside the circuit from positive terminal to negative terminal, in this way, if we get, when we address this resistance as internal resistance, when we put it outside, we are putting this symbol just to show that this is also a resistance offered by the battery. So when we put it outside, we can put like this. Outside the circuit it is from positive terminal to negative terminal. Effect of internal resistance is that only. Okay, so if we mark like this is a sign convention. Okay, sign convention we will study in detail. Okay, so if we mark like this is 6 volt. The drop here is nothing but 3 volt. Okay, 3 volt and this is 9 volt. So terminal potential difference or terminal voltage is nothing but this 6 volt. Okay, and other part of the battery is taken by internal resistance. So the difference between EMF and terminal voltage is nothing but EMF is the voltage across the same terminal A and B when no current is flowing, and terminal voltage or terminal potential difference is nothing but the voltage across the same terminals when current is flowing. Okay, when current is flowing. So we will write that. Okay, terminal potential difference is the potential across the terminal of battery when current is flowing in the circuit. When current is flowing in the circuit. Clear? Okay, so that is the only difference. EMF is when current is not flowing. Here it is current is flowing. Right? Note it down. Now, just we will learn one circuit technique. Okay, we have studied a lot of circuit techniques to deduce resistances, complex resistances. Now we are not yet touched KCL, Kirchhoff's current law, Kirchhoff's voltage law. Okay, nodal analysis. Okay, all these things we will see after the cell. Okay, that is the real very interesting topic. Now before that, I will give you some introduction about as a simple circuit solving technique. Okay, just suppose, see, if we have a terminal here, a resistance, a cell, another resistance, then another cell, then this is another terminal. Suppose if this is 2 ohm, this is 4 volt, again this is 2 volt. Suppose if this is again 2 ohm. Now suppose current is flowing like this, say for example 2 ampere. Current is flowing like this, 2 ampere. Now you can understand that a circuit cannot stand alone like this. If a part of circuit, if we take like this, current will not be flowing also. Current will not be flowing, correct or what? Current will not flow. So this will be a closed circuit. Definitely other parts are there. So remaining parts we don't have absolutely any idea what is the remaining part. But we need to analyze this part. The question is like that. Say for example, if a capacitor, already you have studied about capacitor. Suppose a capacitor is connected like this, then what will be the voltage across the capacitor? The voltage across the capacitor will be the voltage across this terminal only. Okay, Q is equal to CV. Like that, when you study what is the voltage across these two terminals, that voltage will be applicable for this capacitor also. Okay, just for example I am telling. So likewise we will have lot of use just by analyzing this part of the circuit. Okay, so how to analyze? Suppose if we put this terminal as A, this terminal as B. The potential at this terminal is A, the potential at this terminal is B if we take. This is how the current is flowing. Now I am going to give you a small introduction about the sign convention we are going to follow throughout this chapter. You can follow the same sign convention so that there won't be any confusion. Okay, when we move to KCL, KVL, this is going to come like anything. Okay, enormous ways, enormous amount, this will come. So if the current is flowing in this direction, current flows in from higher potential to lower potential. Okay, so plus minus, I said inside the battery it is moving from lower to higher. That is only for that specific inside only we need to consider. But everywhere, okay, even if we connect the battery also, simply you need to take in which way current is moving from higher potential to lower potential. So plus minus. So already this is plus, this is minus. You can say plus minus, then minus plus. It is coming like this. So current flows from higher potential to lower potential. When we consider, we can take this VA as positive, VB as negative, because we are taking this as current is moving from higher potential to lower potential. So when you take a path in this way, we can write like a VA. When current is flowing 2 into 2, this is going to be 4 volt. First is plus, next is minus, so you can take like a 4 volt. This is a sign convention. You can take in the other way also, but follow one sign convention. Okay, then here plus minus we have taken, so take 4 volt. Then plus minus 2 ampere is flowing like this, so we can take 4 volt minus 4 volt. Here minus plus, so we will be taking 2 volt minus VB is equal to 0. Okay, so this is a sign convention. Okay, this is a technique to solve these kind of circuits also. Okay, so now what is the potential difference VA minus VB? If we take, potential difference is nothing but 4, 4, 4, 12. 12 minus 2, so this is going to be 10 volt. So the potential difference across these two terminal is nothing but 10 volt. 10 volt. Now you see, these batteries are connected in reverse potential. One is plus minus, another is minus plus. These resistances are in series. Now I am going to replace it like this is plus 4 volt, this is minus 2 volt. Just I am telling like based on the polarity, or you can take like this is minus 4 volt, this is 2 volt. All the things are based on our convention. So this is going to be 2 volt plus minus. So I don't disturb the polarity. This is more, this is less. So I maintain the more one's polarity and maintained as such and put the difference. This is 4 volt, 4 ohm. Now I maintain this as VA, this as VB, and I put the same amount of current also I can assume here. I can understand same amount of current will flow because two batteries I connected like this. One amount will be cancelled by this, and this is series connection also, so same amount of current will flow. So now if we take VA, okay, VA, then this is nothing but 2 plus minus, this is going to be 8 volt, 2 into 4, 8 volt minus 8 minus VB is equal to 0. So VA minus VB is equal to 10 volt. Same effect I will be getting. Okay, if I put the batteries, if I put the resistances, everything in series, if I solve and put, I will be getting the same set. Now instead of this path, if I take path in the reverse direction, what will happen? Now I will be considering this as at higher potential, this at lower potential. Current, everything must be same. This is a circuit solving technique. Okay, this is a circuit solving technique. Okay, a convention. Okay, along with the sign convention. So if this is VB, this is VA, and if I am taking the path like this, I can take this as positive, this as negative. We will see whether any change will come to the answer. Okay, don't disturb the current. In the direction of current, you can take the sign also. Okay, now I am taking VB plus minus. We are always taking the second sign. Okay, plus minus, so minus 2. Then here I am taking, this is minus, this is plus, so I am taking plus 4 volt. Then here minus plus, I am taking 4. Then here what is happening? Minus plus, so I am taking plus 4. Okay, then minus VA is equal to 0. Now look here, if I bring this side, VA minus VB is equal to what? 4, 4, 4, 12. 12 minus 2, 10 volt. Same answer I am getting in all these cases. Okay, so any path can be chosen. Any path can be chosen. Any path can be taken. Don't disturb the current direction. Mark the signs in the direction of current. Plus, minus, plus, minus. Take the cell sign also in the same way. Then wherever we are starting, just take it as positive, take the other one as negative. Okay, then write like this is what I into R, I into R, I into R. Take the sum of voltages, sum of the voltages with the proper sign. We will be able to find the potential difference between 2 points. Clear? Right, note it down. Okay, now we will see about terminal voltage, how to find terminal voltage. Just when we got if this is R, this is small r, this is E. Okay, so when you know the resistances, if you are able to calculate the current and all, you will be able to find. So just like directly a direct formula to find potential difference across the terminal or terminal potential difference, how we will take. Suppose if this is terminal A and if this is terminal B, okay, that is same as what? Terminal potential difference. Actually VA minus VB will be what? VT, terminal potential difference. So same way we will take, suppose if the current is flowing like this, plus minus current plus minus. So now we will take from this VA minus E plus IR minus VB is equal to 0. Okay, I took with which path? I took this path. Correct or what? Now if I put VA minus VB is equal to E minus IR. Okay, so this is what? Terminal potential difference. So terminal potential difference VT is equal to E minus what? IR. E minus IR. So this is the general formula for finding terminal potential difference. Now, okay, clear? Note it down. Okay, so this AB is same as this one, same as this one. So if current is flowing through this, I can say this is A, this is B. Same way if we take VA, in the same way we will take VA, current is flowing in this direction, minus I into what? R, then minus VB is equal to what? 0. So VA minus VB is equal to what? Terminal potential difference is equal to what? I into R external. So I have one more formula. Okay, terminal potential difference is nothing but current into R external. Clear? Now suppose if I put another resistance, what will happen? We need to take the total resistance. The terminal potential difference is not the voltage across any one resistance. Terminal potential difference is the voltage across full external circuitry. Okay, whatever you get here, whether series resistance or parallel resistance or whatever it may be. Okay, terminal potential difference is nothing but the potential difference across the external circuitry. That is what? R external. So this R external can be R equivalent, okay, if there are more resistances. Okay, clear? Now suppose current I, EMF, internal resistance, external resistance. So terminal potential difference is nothing but E minus I into R. Okay, now what is current here? Current is nothing but E by R plus R. E by R plus R. So terminal potential difference is E minus IR. Can we substitute in the place E minus E by R plus R? Okay, then from this we will be able to find the relation for smaller resistance, internal resistance R also. Okay, clear? So first what we will do is, from this we will do like we will maintain IR. So E minus terminal potential difference. Okay, so internal resistance is E minus terminal voltage divided by what? I. Okay, so this is a formula for finding what? Internal resistance. Clear? EMF minus potential difference, terminal potential difference divided by I. Note it down. Okay, now internal resistance R is equal to E minus potential terminal voltage. I is equal to E by R plus R, that is also fine. At the same time, if this is the terminal potential difference, we can write Vt by R also, Vt by R also. So in the place of current, I can replace Vt by R also, Vt by R also. So internal resistance is nothing but E minus Vt divided by Vt into R. So all these are relations to find internal resistance. Clear? So need not by heart anything, but just understand it. Vt is equal to E minus IR. It will be easy to remember, and it will consume less time if we try to follow those equations. Okay, clear all of you? Look here students, now a cell can be there in various situations. Generally we said terminal potential difference or terminal voltage is nothing but V is equal to Vt is equal to E minus IR. Okay, Vt is equal to E minus IR. So that is okay with the discharging of a cell. Discharging of the cell is what we have seen so far. That is, this cell will be supplying current. Okay, cell will be supplying current to the whole circuit. Correct, cell will be supplying current in the sense, you know its meaning now well. Okay, it is giving energy to the electrons and making it to pass through the circuit. So this is same as discharging of the cell. So in some occasions simply they will be saying that a discharging of a cell is happening. Discharging of a cell. So but just by seeing that word, we need not get confused that this is something new. This is very same as what we have discussed. This is nothing but discharging of the cell. If we take, this is what? This is R. Say current is flowing in this direction, internal resistance EMF E. Same as discharging of the cell. This formula is applicable here. Okay, so discharging of the cell, we can say terminal potential difference is E minus IR. Okay. Another occasion is there, charging of a cell. Charging of a cell means here I will be marking current in this direction. I will be marking current in this direction. In the previous case, okay, just a few minutes back, we have seen a resistance, a voltage, resistance, and we marked it like this. Here whichever cell having more polarity, that we have accepted. Same way, if there is a bigger cell, okay, a stronger cell, a powerful cell, a cell which is having more EMF, a cell which does more work, connected, if we connect in the circuit, what will happen? That cell is powerful than this. So that will deliver the current, and this cell will be forced to receive the current. Just like a circuit which I will draw here. If we take a cell, this is our regular cell, okay, our cell under consideration. Now we have connected another cell like this, okay. So this one is having bigger polarity, okay, more. So what will happen? Instead of current flowing in this direction, current will start flowing in this direction. So that is what is called the charging of a cell, okay. How we will charge? We will charge by connecting the cell to a cell with a better EMF, okay. Correct or what? We take knowledge from more knowledgeable person, but even we have some knowledge. Same way, cell is taking what? EMF from someone else. That is what is charging of the cell. So same technique we will apply here. We will consider this as A, we will consider this as B. Current will be flowing in this direction. So plus minus we will be taking. So in this way we will calculate. So V terminal is nothing but VA minus VB. The potential difference across these two terminals, that is what? Potential, okay, terminal potential. So what we will take? VA, okay, keep it there. VA, then plus minus EMF of our cell, current is flowing, so minus IR, then minus VB is equal to 0. So when we take VA minus VB, we come to know E plus I into R. So here, in this case, in the case of charging of a cell, we are getting terminal voltage as E plus IR. Terminal voltage is E plus IR. Clear? Okay, so discharging of a cell, as usual, same thing which we have seen so far, E minus IR. Only for charging of a cell, terminal voltage will be E plus IR. Okay, clear? Note it down. This is the third case. So first case is discharging of a cell, second case is charging of cell, third case we are taking open circuit. So open circuit is nothing but there is a cell, its internal resistance. This is a switch. If we switch on, what will happen? Current will flow. When switch is off, no current, okay, no current. So what happens here? Open circuit, this is called open circuit, no current is flowing. Switch is on, this is not a closed circuit. So no current is flowing, so I is equal to 0. So if we take in the same way, terminal potential difference is what? VT is nothing but VA minus VB, that is the potential across this terminal, that is the potential across this terminal, everything is same. Okay, so if we take VA minus E, here this is nothing but 0, okay, minus VB, okay, so is equal to what? 0. So VA minus VB is equal to E, same as terminal potential difference. Okay, so here in open circuit we have EMF is same as terminal potential difference in open circuit when no current is flowing. Actually this is what the terminal potential difference, that is EMF is the terminal potential difference, or EMF is the potential difference across the points, across the terminals when no current is flowing. Okay, that was the definition we have seen. Same thing. Okay, clear? Okay, so this can be written like a cell is open circuited. Okay, likewise also we can take. Okay, fourth point is cell is closed circuit. Okay, short circuited. Okay, cell is short circuited. Okay, cell is short circuited means, short circuit means actually if there is resistance, resistance will take some voltage, and definitely the current in the circuit also will be less. Say for example, if you take a cell, internal resistance is there anyway. If you connect that to an LED, if you connect this to LED directly, okay, sometimes this will burn off. Okay, if we directly connect a battery. So for that, if you take a resistance, then LED will glow. Okay, with the R resistance, if resistance is there, it will glow, otherwise it will burn off. Why? Because LED is having a capacity. Full current if it takes, it will burn off. Okay, if resistance is there in the circuit, less current will flow, LED will not burn, and LED will glow also. Okay, so if you have done small circuitries, small projects, okay, you might have seen this. So same way, and moreover you might have seen, if you read in the newspaper like this fire accident, something happened, then they might be writing like suspecting short circuit. Okay, short circuit is what police is thinking, something like that you might have seen. So short circuit is nothing but, so a battery is connecting directly without any resistance. So sometimes that causes damages. So here cell is short circuited means this is our cell, internal resistance is there, so connecting without any resistance. So in the place of resistance we are simply connecting a wire. This is E, this is R. So current will be flowing. What is the current here? E by resistance. Resistance is nothing but only internal resistance. This is the maximum current. Maximum current occurs when short circuit, that is external resistance is equal to 0. External resistance is equal to 0. Okay, what is the same way if we try to calculate A, B? So when the cell is short circuited, no external resistance here, maximum current you will be getting I, because I is equal to E by R, otherwise one external R also will come here. So R external is 0 here, we haven't connected any resistance, directly connected, that is what short circuit means. So we will find the terminal potential difference or terminal voltage in the same case here. Okay, so which direction current is flowing? Current is flowing in this direction. Okay, so we will take VA, current is flowing in this direction, plus minus E. Okay, then plus IR minus VB is equal to 0. So VA minus VB is equal to E minus IR. So is it same? The problem is I is equal to E by R. So we will substitute here. So VA minus VB is nothing but terminal potential difference is equal to E minus E by R. E minus E by R, and a R is here, E minus IR. So I is nothing but E by R will get cancelled, we will be getting 0. So terminal potential difference is equal to 0 in case of short circuit. Terminal potential difference is equal to 0 in the case of short circuit. Okay, so students, EMF is nothing but, I'll tell you the definitions. EMF is the work done per unit charge in order to make it in the closed circuit. EMF is the terminal potential difference, or EMF is the potential difference across the terminal when no current is flowing. Same case with the open circuit. Okay, EMF is equal to VT. Okay, when no current is flowing. Okay, then terminal potential difference is nothing but that potential difference across the terminal of the battery, or same as the across the terminal of external circuitry. There could be one resistance, there may be more resistances also. Okay, charging and discharging, open circuit, short circuit. Charging is nothing but we are making a bigger cell to charge our cell, the cell under consideration. So there the terminal potential difference VT will be coming as E plus IR. Okay, E plus IR. Okay, so charging is nothing but V, terminal potential difference is E plus IR. Discharging, VT is equal to E minus IR. BT is equal to E minus IR. Short circuit, what is VT is equal to 0. Open circuit, VT is same as the cell. Okay, EMF. Okay, and EMF is nothing but work done, okay, per unit charge to make it in the closed circuit, EMF. Okay, clear? Right, so we will conclude the session. From this session we will need to do more numericals, and we need to analyze some graphs. Then combination of cells also will come, that we will see in the next session. Thank you students, bye bye, good luck.